In this video, I'd like to just focus on the last parts over here. Now, there are a lot of things being discussed in this chapter, starting off first with um, static electricity, right? Where you have light charges attracting, unlike charges repelling. Um, if there's excess of electrons, then it's negatively charged, so on and so forth. And then you have a whole list of those equations, starting off first with Q equals to IT. Then you have V equals to W over Q, where W stands for the work done on energy, which is charge. And then after that, for resistance, we have already studied V equals to IR. Of course, the versions that you see inside the textbook would look like I equals to Q over T, and R is equals to V over I, right? This over here is just the version that we use in class. But this one over here, the last one over here, is a bit different. It does tell us that, hey, there's actually one more formula that you need to know for resistance. And that formula is R is equals to rho L over A. Now, what is this? Now, I know that I can find resistance by taking the potential difference, let's go a bit higher, by taking the potential difference across the component and the current going through the component. If I were to divide those two things, I can find resistance in ohms. Great. I know the SI unit ohms. I know this one is volts. I know this one is ampere. I just realized that my arrows are going the wrong direction. I'm sorry. That's my point. So I know that part. Okay, but resistance also depends on three other things. It depends on this, and that. One of these three. The three things are resistivity, length, and cross-section area. Resistivity talks about the material, what it's made of. This resistor, what's it made of? There's certain metals which, while they do conduct electricity, they don't conduct very well. There's a low, no, there's high resistivity because it's hard to go through, right? If I have something that's very easy for current to go through, well, it has low resistivity, right? And that makes sense, right? It's logical. Now, length and cross-section area is where we get most of our questions, where we have to work it out and compute it. And it could look something like this. Well, in this case, we just need to use a formula to find resistance equals to rho L over A. This is my resistivity, right? So let me just write down the whole formula again, because that's the practice you should have. 1.6 times 10 to the power. I'm going to pause this and just go forward. Ta-da, there you go. All right, just remember, if this is going to be in cross-section area, right, my SI unit is meters, right? Everything else is in meters. Can you see that? This is in mm, so I'm going to convert it. M over here being my prefix 10 to 1 negative 3. Square that, you get this. All right, so it could be in this type of calculation type of questions, but the more common questions would look more similar to, well, this. Right? It doesn't quite tell you the resistance. There's nothing you can quite calculate over here. How do you do this? So I'd like you all to consider this like a logic question where you can answer it very logically by doing this drawing. Okay, so I have this copper wire, 10 meters long, and it has a cross-section area of 1 mm squared. So 10 meters, and my area is 1 mm squared. What happens when I have this same wire that is 5 meters long and a cross-section area of 2 mm? So remember the formula? Now we're going to see that for R and L, these are directly proportional and these are inversely proportional. And even if you don't like the mathematics of this, right, we can realize that it's actually it makes a lot of sense. Here's why. Link the idea of resistance with the idea of difficulty. Which is more difficult, running 1 km or running 7 km? Well, the longer it is, the more difficult it is, right? So the greater length, the higher resistance, right? This is bigger, that'll be bigger. Longer, more difficult, greater resistance, right? But what about if, let's say, you're trying to walk through a pathway? You have this narrow pathway, okay? You're trying to get through over here. As compared to this wider pathway, we're trying to get through there. Which is easier, this over here or that over here? Imagine if there's a lot of people beside you all trying to squeeze through. Which one would be easier? The one which is squeezier or the one which is more spacious, more spread out? You can see clearly, right, that once you have a place, if you look at from this side, where the cross-section area is small, it's more difficult, high resistance. And when there is a greater, larger, wider cross-section area, the difficulty is reduced, the resistance is reduced. The greater the cross-section area, the lower my resistance. So if this is big, this is small. If this is big, this is also big, right? So just from this logic alone, let's see how we can apply it over here. So let's go down here. I have 10 meters long and only 1 mm cross-section area. Let's draw the next one. What if it's 5 meters long? 5 meters. And now what has happened to my cross-section area? It's become wider, right? It's now wider. And this is 2 mm squared. So let's compare. How did my length change? My length changed, it got divided by 2, correct? What has happened to my cross-section area? It has multiplied by 2, correct? Multiplied by 2. Okay, so far? So, if I remember that if length is about, the longer it is, the harder it is, the shorter it is, the easier it is. See here? If my length was divided by 2, my length was halved. Hey, it should be lower resistance, correct? And lower by how much? It's also halved, right? Directly proportional. So the idea would be the resistance of this new one over here, this resistance over here, it will be the original resistance. Okay, the original resistance, and you divide by 2 first, right? Because it's halved. And then what about this over here? What about my area? Did it get easier or harder? It got easier, right? Because it got wider, right? So lower resistance. If this is multiplied by 2, then in terms of resistance, because it's inversely proportional, it will be divided by 2, correct? Now this looks really weird. We usually don't write that, right? What we usually write would be something that looks like this. Times half, then times half, right? Because we're going to write divided by 2. This first half over here is for this part over here. This one over here is for this one over here. Okay, so the logic just tells me that it became shorter, it became wider. I'm going to have a lower resistance. And how much lower is the resistance? Well, it's going to be R over 4, right? My new resistance in terms of R is going to be R over 4. So let's try another one. But this time, I'm going to tell you the original resistance. Let's say this wire over here is 10 ohms, it is 1 meter long, and the cross-section area is 1 mm squared. Now, let's say that I want to know what would be the resistance if I have the same material, so the wave resistivity the same, but instead of 1 meters, it is 3 meters long. And instead of 1 mm square, it's only 0.5 mm square. 0.5 mm square. Now, take a moment to think about the logic. From 1 to 3, did it get harder? Did it get more difficult or less difficult? Has my resistance increased or decreased? What do you think? Right? Here we go. In terms of my length, I remember that the longer it is, the higher the resistance, correct? Because it's directly proportional. It got 3 times as long, it's going to be 3 times as hard, correct? My resistance would be tripled times 3. Okay, so that's looking at length. What about if I look at my cross-section area? What happened to my cross-section area? Hey, from here to here, I have seen that my cross-section area is halved. it got divided by 2, correct? So what does it mean for my resistance? Instead of it being bigger, it got smaller. It's going to get more difficult. My resistance will increase. Kind of like the reverse of this, right? I see divide by 2 in terms of my area, but I know that it means it's times 2 in terms of my resistance. So what is my new resistance? I would say the resistance of the wire, right? The new wire will be 10 ohms, right? Multiplied by 3 for my length. And about my cross-section area, it's not divide by 2, it will be times 2. That gives me the resistance for this new, longer and thinner wire to be 60 ohm, right? That's the logic behind it. Oh, by the way, something that could help with the divide and everything is that you could also think of it as, how did I go from 1 to 0.5? Maybe another good way is you can think of it as, instead of divide by 2, it was multiplied by half, right? And you see, the reciprocal of this, once you have the reciprocal, it becomes times 2. Now, this is especially important, especially when you see the next question, right? I mean, once you see the next question, it becomes a bit more clear why it might be better to use this instead of this. It is still divide by 2, right? It's half of it, right? But keeping in this fraction, keeping in terms of a multiply rather than divide, could be more useful, right? So let's take a look at another question, and it should be over here. Let's say we have the first resistor. I say that this Y over here, this resistance is 5 ohm, where this is 2 meters long and the diameter, not cross-section area, is 3 mm. If I have used the same material, but this time it's 3 meters long and the diameter is 2 mm, what will be the resistance? Okay, so easy part first is, hey, I know about this part. Hey, how did I get from 2 meters to 3 meters? What do I multiply to get 2 meters to 3 meters, right? So we can take it as multiplied by 3 divided by 2, right? That's how I get from 2 to 3. Okay, comfortable with that fraction? So that's for the length. Now for the cross-section area. Oh, this is not cross-section area, this is diameter. How do I go from diameter to area? Remember, this is a circle, right? Cross-section of these things are circles. And the one thing to remember is that area is going to be proportional to the square of the diameter, right? Now this is mathematics, right? Similar to what you understand for A equals to pi r square or pi d over 2 square, right? What's important now, just for the physics part, is that the area is going to be proportional to diameter square. So when you actually see this over here, right, you cannot use 3 to 2 because the area would be similar to pi 3 square. This over here would be pi 2 square. You see that? So in terms of pi, this area would actually be 9 pi. And this over here would be 4 pi. Don't be scared. Don't be worried about the pi part. Okay? It will cancel out. Don't worry about that. Okay? Now, how do I go from 9 pi to 4 pi? What do I do? Well, think about it, right? If to go from 2 to 3 is I divide by 2 multiply by 3, how do I go from 9 to 4? I can divide by 9 to go to 4, correct? So in terms of my area, this over here, the change would be multiplied by 4 over 9. Okay, that's how I changed. That's how the area changed. It was you multiply it by 4 over 9. All right, so that's for the change of area. That's for the change of length. So what happened to my resistance? So I'll say the resistance of the wire will be equals to 5 multiplied by, what do I multiply by? Okay, let's go length first. So length multiplied by 3 over 2, does it make sense? Yes, because it's directly proportional, right? 3 over 2. Now, the next part, do I multiply by 4 over 9 or do I take the reciprocal? like what we did early on up there, right? The idea is the idea of reciprocal, right? Instead of half, it becomes 2. Likewise, over here, instead of 4 over 9, it's the opposite, right? It's a reciprocal. So times 9 over 4, because it's opposite, right? If my area got smaller, the difficulty gets smaller, correct? No, all right? When the area gets smaller, the difficulty gets greater, right? It got squeezed, right? So it's a smaller area, it's going to be harder, it's going to be the opposite direction. That's why if my area got smaller here, it means my resistance is going to go up. Here is 4 over 9. Once I think of my resistance, it will be 9 over 4. And what we get? If intrinsic fig would be 16.9, if you get the whole thing, it would be 16.875 ohms, right? So that's the idea of this whole thing, of the logic of it, right? All right, let's try one last one before we go. Let's just see if we can catch the logic without much calculation, right? Can you see? This is 10 ohm. So if you want to pause it now and take a look at it. This is 10 ohms, okay? This over here, same material, but it is only 1 meter, and my cross-section area is 4 mm squared. How would you do it? 5, 4, 3, 2, 1. In terms of length, I divided by 5, correct? Or, as you would say, like this, correct? That's how my length changed. What about my area? This was a multiple of 2, multiplied by 2. In terms of logic, hey, it's shorter, it's going to be easier, right? My resistance will divide by 5. In terms of area, it got wider, it's going to be easier. My resistance is going to divide, it's going to drop again, right? So, what's the resistance of the shorter wire? 10 ohms divided by 5, correct? Which is written this way. And what about the area? Do I times 2 or did I divide by 2? Did it get easier or harder? It got easier, right? So, divide by 2. Or, as you have done before, times half. Therefore, my answer will be just 1 ohm. Right? Hope you caught the general idea of this logic of these questions. There's much more to say about these things, but this is a good 20-minute overview of what you should understand for this part of current electricity on resistance.